For my Phases of Matter project, I am doing the natural phenomena of freezing rain. But before I explain freezing rain, we should go back to the basics on how rain is formed through the water cycle. So firstly, water is a liquid and flows. It doesn't have a definite shape. In fact, it conforms to the shape of the container it is in. In this case, water in lakes, streams, and rivers are in crevices or indents in the Earth's surface. The water has translational movement, meaning they move away from each other but stay in a liquid together. Now some particles move away from the lakes, streams, rivers, or any body of water, in this case through evaporation. Evaporation, not boiling. The difference between evaporation and boiling is that evaporation only occurs at the liquid gas surface and at lower temperature than the boiling point. And boiling occurs throughout the entire liquid and at the boiling point. Therefore, the water evaporates under the heat of the sun and goes into the atmosphere. Because the water molecules that evaporate have higher energy particles, the remaining liquid in the lake or pond has a lower kinetic energy than before the evaporation occurs. The water evaporation in the atmosphere from the bodies of water show the kinetic molecular theory through its physical properties. The water vapor's volume is extremely small compared to the atmosphere. The water vapor particles move too fast for any attractive or repulsive forces to occur. The water particles move in a straight line unless it hits the container or another molecule. Collisions are elastic, and particles act like hard spherical objects. As the temp goes down, the average kinetic energy goes down as well, causing the water vapor to condense. Therefore, as the water vapor moves up in the atmosphere, it starts to cool and eventually condenses due to the cooler air. This is because the higher in the atmosphere you are, the cooler it is. Then the small droplets of water start to stick together and form clouds. Those clouds then produce precipitation. The cycle then just keeps repeating and repeating. For different precipitations to form, the precipitation has to go through phase changes based on the temperature and the time it is in said temp. The bottom of the heating curve is a solid. As it moves up the heating curve, the energy goes into changing the temperature, thus the temperature rises. After the temp rises, it hits a plateau where the solid melts, forming a liquid. That is due to the energy going into melting, not rising the temp. Then the liquid starts to warm up and the temperature changes. Then it plateaus again because it starts to boil into a gas. The gas then begins to warm up. Just as you go up the heating curve, you can also go back down and condense a gas into a liquid and freeze a liquid into a solid. Now on to the different types of precipitation. Snow forms in air that is 100% below freezing and never warms up or cools down. Sleet forms with a pocket of warm air. This allows for the snow that it starts out as to melt into a liquid. But at above 3,000 feet, another pocket of air is present, except it is below freezing. This is enough time for sleet to freeze from the liquid and hit the ground as a solid. Rain forms with air being above freezing until it hits the ground as liquid. Now freezing rain has a pocket of above freezing air melting the snow into a liquid, just like sleet. Then at around 2,000 feet, the air becomes below freezing. But while it is cold enough to freeze the rain solid, the structure of their molecules remains liquid. This is due to supercooling, a strange state between solid and liquid. Now, for freezing to occur, a nucleation point has to be present. Nucleation is a point within a liquid that starts the formation of crystals. In other words, it starts the freezing. In clouds, snow forms around little pieces of dust or other particles that act as a nucleation point. The snow crystals then form around that center point. Sleet forms around the same pieces of dust or particles, but it has enough time to freeze and become a solid. For freezing rain, because it is going through relatively still, clear air, and there isn't enough time to freeze, nucleation doesn't occur until it hits the surface and freezes on contact. In this case, the ground, vehicles, buildings, trees, electrical lines, etc. Then the rain freezes into ice, a solid. The ice particles do move, almost like a vibration, and they are packed together into a set shape. Water is weird in that it is less dense as a solid than as a liquid, meaning ice floats in water. But most liquids are more dense as a solid. The attraction between particles is very high, but as you move away, they're less influential. The more energy, in this case heat, put into the solid allows for those attractions and bonds to be broken and for it to become liquid or sometimes even a gas. Now, crystalline ice is where the particles are arranged in a geometrically repeating pattern, most likely cubic or hexagonal. Most ice you see naturally is crystalline ice. This is like snow, ice you use for a drink, freezing rain, and the polar caps. Lastly, it breaks along set planes. Now, amorphous ice is particles arranged in disorder. In other words, there is a lack of any arrangement. Thus, they break in random fashion. But they are still locked in a phase. This ice is found in space. Because the ice is organized in different ways, the amorphous ice and the crystalline ice are allotropes of each other. Allotropes are common in everyday life in chemicals. For example, carbon. It can be a diamond, graphite, charcoal, and even carbon-60. Although amorphous ice isn't common on Earth, it is in space. Thus, it is an allotrope of water. Now I'll get into the objectives that I didn't cover through freezing rain. So, Objective 6 describes the changes in vapor pressure with changes in kinetic energy and changes in atmospheric pressure. So, vapor is a material in a gas phase coming from a liquid or a solid. Vapor pressure is the pressure of the vapor coming from the liquid or the solid. As kinetic energy increases, vapor pressure increases, and more particles are moving fast enough to break the bonds that held the particle in the liquid or solid. Boiling occurs when the vapor pressure equals the atmospheric pressure. Objective 7 describes the effects of changing external pressure on the boiling point. The pressure you put on one part of the liquid is the same throughout the whole liquid. Nascent bubbles form on surfaces of a liquid and solid where gas molecules can collect. It's not the atmospheric pressure pushing on the bubbles, but the atmospheric pressure which pushes on the liquid, which pushes on the bubbles. Higher atmospheric pressure pushes on the liquid, which according to Pascal's principle, distributes pressure equally throughout the liquid and pushes on the nascent bubble. If the nascent bubble pressure is less than the atmospheric pressure, the bubble collapses. Therefore, there is no boiling. If the nascent pressure is greater than or equal to the atmospheric pressure, the bubble will grow, which allows boiling. Objective 13 describes how the strength of the intermolecular forces, external pressure, and available energy affects the state of matter of various materials. The three things that affect the state of matter are intramolecular attraction, available energy, or temperature, and pressure. The stronger the intramolecular attraction, it is more of a solid. The weaker it is, it's a gas. The lower the available energy, it's a solid, and the higher it is, it's a gas. The higher the pressure, usually it's a solid, and the lower the pressure, it's a gas. Objective 14 describes the motion of particles in a plasma state, including the relationship between their kinetic energy and the effect of attractive forces. If enough energy is available to break electrons away from individual atoms in enough molecules, this happens. This creates a sea of free electrons and cations. Plasmas flow like liquids, but plasmas conduct electricity very well. Objective 15 describes the motion of particles in a Bose-Einstein condensate, including the relationship between their kinetic energy and the effect of attractive forces. It forms at a very low temperature, just above 0 Kelvin. Normal boundary between atoms is caused by electrons repelling. But when those electrons slow down, then the electron fields can overlap. That means that the boundaries between atoms are not extreme, so the atoms overlap, which forms a superatom. Now I'll be showing you my demo, which will demonstrate supercooling. Now I'll go over the 5 questions about my presentation. Does evaporation or boiling occur in the water cycle? Evaporation. How high is a layer of below freezing air to form freezing rain? (2,000 feet). What has to be present for freezing to occur? A nucleation point. Where is amorphous ice most commonly found? Space. What temperature does a Bose-Einstein condensate occur? Just above 0 Kelvin. This is my works cited. Thank you for watching my video. See you guys in class!